Okay, so our final chapter, chapter 15, is going to be very reading intensive. And so I suggest that everybody go read this chapter. This is going to be very important for you guys to read this. Uh, but I'll go ahead and lay out some of the mathematical equations that we're going to be using in this class or in this chapter. So very quickly, the, the first property of a wave that you're going to need to know, and one of probably the most important one, is that the velocity of a wave is going to be equal to its wavelength times its frequency here. So we are combining two of its basic properties to get its velocity here. As you can see, wavelength is going to be equal to is going to have the measurement of meters, and frequency is going to be 1 over seconds, and so that easily combines into meters per second, or the velocity of a wave. So next things up is we're going to have to talk about wave functions, and so wave functions in this case, we're no longer going to have a function of just of this function is going to be a function of y, but it's going to be dependent upon x and t in this case. And so in this case, we're going to have two variables that we would have to plug into each one of our equations in order to get these equations. So now in this case, we have that for a function of for when this is x, and you talk about what this is equal to from peak to peak, or from trough to trough, this is going to be our lambda. And then for if we're talking about this as a function of time, then this is going to change. And so then you measure this out, and then your period is for when it completes one total cycle. So then for when it comes from here, usually this is going to be a different graph. So let's draw this out. So for when we're talking about a period t, usually this is going to go like this, like we saw in our oscillations chapter. And so when it completes one cycle from here to, I'd say, about here, this is going to be our period t from these two spots. And so then you have to convert your period to your frequency, and we saw that this is just you just take 1 over t to get f, and then you can plug those in to get your velocity of your wave, and you can see how far it travels. So let's now give the equation for our waves here. And so the basic equation is going to be y of x and t is going to be equal to a cosine of omega times x over v, which is our position of our wave over its velocity, minus the time here. And so this is our basic wave equation. And so then one thing that we can do to manipulate this equation is remembering that omega is going to be equal to 2 pi f, or the fact that omega can be equal to 2 pi over t. And so plugging that in will give you a slightly different equation. So another way to write this equation is that y of x and t is going to be equal to a cosine of omega t, or no, that's going to be the minus part, kx minus omega t. Yep, and where in this case k is going to be equal to 2 pi over over lambda in this case, and omega again is going to be equal to 2 pi f, and or you could say that this is going to be equal to v times k. And so if we want, we can manipulate this equation to say that this is a cosine of 2 pi over lambda times x minus 2 pi f times t. Or if we want, we can go ahead and plug this in, and we can say that this is going to be vkt. So any one of those forms would work, and any combination of those forms can work. So another thing we're going to see is we're going to end up wanting the wave equation. This is going to be another useful formula, so I'm just picking out the formulas here. So if you take the second partial derivative of our wave equation here, and we have to use partials here because it's a function of two different things. So that's where this is coming from. So the second derivative with respect to position is going to be equal to 1 over v squared times the second partial of y, x, and t over dt. This is going to be the partial of dt squared. And in this case, for waves on a string, you can say that v is going to be equal to f over mu, or the square root of that. Okay, so if we're talking about this moves us forward in our study of waves, where we have to talk about power here, and so going ahead and saying that you can find your detailed description for power, and power is going to be equal to 1/2, because we're taking the average here, times the square root of mu f, and then we have to multiply it by our angular frequency times its amplitude squared. And real quickly, we can use an inverse square law for intensity. So if we're comparing two intensities of waves, they follow an inverse square law like gravity does, where this is going to be equal to equal here to the it's going to be inversely proportional to the square of the distance from the source. So this is going to be a very useful equation here. So in other branches of physics here, so this is important. Another thing that we're going to have to talk about is wave superposition. So just like we can superposition forces, in this case, we can also superposition waves. So this is another little analog here. So if we have two different waves, we can find their combined wave function. Y of x of t is going to be equal to y1 x t plus y2 x of t. And so very easily you can take two wave functions and add them together to get a third wave function. You can do this with basically any number of wave functions and use linear algebra to find these combinations here. Last thing that we have to talk about is standing waves. So we talked about forced oscillations a little bit. If you're inducing some sort of if you're taking, say, like a jump rope, and there are going to be certain frequencies that you exert on this jump rope here, to where you can give it different types of nodes. So at certain points, you're going to end up getting different nodes here. So this is basically just a superposition of when we have 4 nodes. So if you give this enough, or like if you give this enough energy, you'll end up getting a whole bunch of different nodes. So originally, if you're just swinging the jump rope, you get this one large node. But if you start to give it a different wavelength, you'll end up getting a node that looks like this. So where there's going to be a small spot here, and this small spot, or where there's not much vibration, or where these ropes start to vibrate around, is called a node. And these large parts will give us an amplitude of A. And now you can continue on and give this, if you drive it more and give it a bigger oscillation, you'll get 3 humps here and 2 nodes, where the amplitude of the humps is all going to be the same at A, and then the nodes are going to have an amplitude of 0 there. And you can continue on as you drive this rope further and further. I'm just using rope as an example of a wave. If you continue to drive it at a certain frequency, you can add an extra node on here and an extra high peak of amplitude on the end here. So you can continue to do this as many times as you want. And we can mathematically describe standing waves on a string or a rope as we get y of x and t here is going to be equal to a standing wave. So this is going to be the amplitude of the standing wave here. This is going to be this is what this is going to be. This is going to be the amplitude here of sine of kx, and then we're going to have sine of omega t. And this is going to be with a condition that x is going to be 0, so it's going to have a fixed end. And so we can derive the frequencies here. So and the frequencies are going to be derived as a function of the nodes here. So Fn, so n is going to be the number of nodes here, and this is going to give you n times the velocity of these standing waves over 2 times the length of the string. And this is going to, in this case, equal dependent upon n. This is going to be n of f1. So it's going to be where n is equal to 1. So you just basically have to take the number of nodes and multiply it by the first frequency of the node. And so then we can say that f1 here is going to be equal to 1 over 2L times f over mu. And you can go back and see for waves on a string that this quantity here is going to be our velocity. And so we can go back, and this is how we get from here to here. And so this F is going to be the tension in the string, and mu is going to be the mass per unit length. And so then this is our final equation here, I believe, for our chapter. And so, yeah, you definitely have to go through and read this chapter. This is one that is not readily mathematically explained or mathematically illustrated. You have to go and read for yourself what a transverse wave is, and you have to go and look at the actual graphs here, because there's way too many of them for me to go ahead and draw. So this is a chapter that I wouldn't want to say that you're on your own for, but something that you're going to have to read for yourself and internalize for yourself. So go ahead and read this chapter, because this is a good one to read. there's not many mathematical equations, and this is something that you guys are going to have to read for yourself in order to get the same conclusions.